Okay, I decided to make a very short video, which is consists of things that I said at the end of lecture 8.2, but I didn't record, so I was Andre suggested me doing that because in the first 2 weeks we did a lot of algebra starting from set theory and defining a lot of abstract structures. It's a good thing now to summarize what we have done. So we started with sets, uh, which are just collection of elements. So let's start with some set and call it R. So it's collection of elements. So it kind of doesn't have any structure out. And we started with algebraic structures with one operation. So we started with some operation, let's call it star, from R times R to R. Now it may induce some inverses and units like in group and so on, but the important part is the binary operation, and this gives group-like structures. So, so here no structure for sets. Here we have group-like structures. And I didn't define that, but some people for some reason just say set with binary operation without any kind of constraints on magma. But we started with semi-groups, which are associative. So we have semi-groups, semi-groups. Then if we add, so this is associative. If we add unity, so associative here plus unity is a moment, and groups. And groups have inverses, plus inverses. So any kind of structure has more constraints than the previous one. The binary operation has more properties by definition. Then I move to ring-like structures. So ring-like structures, they have two operations. Let's call them class and product. R times R product. So these are ring-like structures. So they have the addition gives a Bilinear group. We have distributive laws for addition and multiplication. That is what's something that relates to operations. And in rings we have associativity of the product, but they're interesting such that are not associative. But the distributive property is the most important that relates both structures. So these are ring-like structures. And these are the rings, and then commutative rings with unity fields, and so on. So let's start from ring and to fields. There are many in between. We were somewhat here commutative rings with unity. So let's say commutative rings with unity. Here maybe we have only rings with unity. This is only ring with unity, commutative with unity. Fields. There are many in between, but we are not stick to that. Then we said, okay, let's fix some R. So R is fixed. So this is the now we talk about structure built upon other structure. So we have R module. So if we have some set V with addition, which form makes it a bilinear. But then we add some scalar multiplication from V R times V to V, R times V to V, and we get module, R module. So we built the terminology for rings because we want to be able to say, okay, we have a commutative ring with unity fixed, and then we do many operations on the space V, which is the R module. And we did a lot of internal stuff, which is traditional elementary algebra, not elementary, linear algebra, like that elementary one which is studied in first year courses, but ours were done commutative rings with unity rather than fields, but many things are very similar. However, we make some additions like dual vector, so from module V we formed like let's say U and V are modules. Okay. This U in the space of homomorphisms. So we have homomorphisms. We have especially in particular V star. So V star is from R. We did tensor product, so V tensor product with tensor product with V. And also did direct sum U plus V. Okay. And then we did algebras, which are modules, but with operation within. So we have addition of vectors, but we don't have multiplication. But if we have a module. So we have plus and multiplication from, let's start in a second. So we have plus times R multiplication, so not 1 but V, and multiplication from R times V to V. So these two form a module, and usually these two form some kind of ring, and together it's our algebra. And we showed the polynomial algebras example, but we formed generic algebras from starting from U is our module, and then we have the tensor algebra. Not U, let's use V when we have one. This is the generic. So this is the tensor algebra. And also lambda. So this is the smallest associative and unital algebra. And if we add the alternating property, we get the exterior algebra. And there is one also important algebra which I didn't talk about, the symmetric algebra. This is the smallest algebra that is associative unital but also symmetric. And this is what we've done. We can also expand this, but something that I will naturally do for manifolds and for cochains. Sometimes we even add some operation from V to V, which has also some rules for itself, like d squared equals 0, but this has some constraints with the other three operations, and if we combine this with, so if we combine D with all three operations, we will get from this thing here, and from here, differential graded algebra. These are usually algebras that are built on the exterior algebra. And so that is an why do we define all of these structures? Because they occur naturally from different fields, and when we isolate the main properties, the algebraic operations that they have, they may come from topology, from anything, but they have some algebraic operations defined on them naturally. And if we study the general theory, we can get general results for any such constructions. And so we did the exterior algebra thing. It's not clear why, but it will be clear when we do differential geometry and especially differential forms, which will be differential graded algebra, very useful for doing calculus and even for physics, which is the physics application, the main topic of this course. Okay. I made it much